radioactivity was discovered in 1896, quite by accident, by Antoine Henri Becquerel. It is the process by which an unstable nucleus decays into a more stable one by emitting radioactive radiation. The most common types of radioactive radiation are alpha particles, beta minus particles, beta plus particles, and gamma rays. The original nucleus is called the parent nucleus, and the resultant nucleus after decay is called the daughter nucleus. For example, plutonium-240 decays into uranium-236 with the emission of an alpha particle. If the parent nucleus exists in nature, the type of radioactivity is called natural radioactivity, whereas if the parent nucleus does not exist in nature and is prepared artificially, the type of radioactivity is called artificial radioactivity.
Let's look at some properties of the radioactive radiation mentioned. For alpha radiation, the emitted particle is a helium-4 nucleus. Its symbol is He42. It carries a positive charge because it contains 2 protons, and it has very strong ionizing power. This means that the alpha particles can easily knock electrons off atoms in any material they pass through, including human tissue, if they enter the body. This is due to their large mass and +2 charge. The second particle is the beta minus particle. It is an electron. The symbol is E0 minus 1. It is negatively charged and it has a strong ionizing power. The third particle is the beta plus particle. It is a positron, the antiparticle of the electron. The symbol is E01. The charge is positive and it has also strong ionizing power. The last particle is the gamma photon. Gamma photons are just electromagnetic radiation. The symbol is gamma 00. They are uncharged and they have weak ionizing power.
We will introduce 3 laws of conservation. The first law is the law of conservation of mass number. The mass number of the parent nucleus is equal to the total of the mass numbers for the final products. For example, uranium-238 decays into thorium-234 with the emission of an alpha particle. The mass number of the parent is 238, which equals 234 plus 4, the sum of the mass numbers of the products. The second law is the law of conservation of charge. The charge number of the parent nucleus is equal to the total of the charge numbers of the final products. In the decay equation shown, the charge number of the parent is 92, which equals 90 plus 2, the sum of the charge numbers of the products.
The third law is the law of conservation of total energy. This law states that the total energy of the parent nucleus before decay is equal to the total energy of the products of the decay. But to apply this law, we need to know how to calculate the total energy of a particle. Here we have 2 cases. If the particle has a non-zero mass, then we will use this formula. The total energy is the sum of its kinetic energy plus its rest energy. The rest energy is the energy of the particle when it is at rest, and this energy is equivalent to the mass of the particle. So, the total energy of the particle is 1/2 mv squared plus mc squared. If we have a massless particle like gamma photons, then the total energy is just h times nu, where h is Planck's constant and nu is the frequency of the photon.
The figure shows the parent nucleus, the daughter nucleus, and the emitted radiation. In radioactivity, the mass of the parent nucleus is greater than the mass of the products, so that M before is greater than M after. Then there is a loss of mass called delta M. so that delta M equals M before minus M after.
What happens to the mass lost due to the decay? According to the mass energy equivalence formula, the loss of mass delta M is converted into energy. The liberated energy equals delta M times C squared. This energy is called liberated energy or disintegration energy.
Now, let's study each type of radioactive radiation. We start with gamma decay. In radioactivity, gamma rays might accompany alpha and beta decays. If the daughter nucleus is produced in an excited state, it returns to the ground state directly by emitting one photon or in several steps by emitting more than one photon. Then, a gamma ray is emitted when the daughter nucleus decays to a lower energy level. The general equation for gamma decay, XAZ star, decays to XAZ plus gamma. The star is used to indicate that the nucleus is in an excited state. By neglecting the kinetic energies of the parent and daughter nuclei, the liberated energy, delta mc squared, is equal to the electromagnetic energy carried by the gamma ray. Example, uranium-236-92 star decays to uranium-236-92 plus gamma. Look at this animation. Gamma radiation penetrates the sheet of paper and even a few centimeters of aluminum, but it is stopped by lead. This means gamma radiation is very penetrating.
Let's move to the alpha decay. This type of decay is a characteristic of a heavy parent nucleus, which means that the mass number should be greater than 200. This is the general equation of alpha decay. If the daughter nucleus is produced in an excited state, it returns to the ground state directly by emitting one photon, or in several steps by emitting more than one photon. Now, by neglecting the kinetic energy of the parent and the daughter nuclei, the liberated energy will be just the sum of the kinetic energy of the alpha particle and the electromagnetic energy of the gamma photons. The forms of the liberated energy are the kinetic energy of the alpha particle and the electromagnetic energy of gamma rays. Look at this example. Plutonium-240 decays into uranium-236 by emitting an alpha particle and gamma ray photons. Look at this animation. Alpha radiation cannot penetrate the sheet of paper. This means that alpha radiation has weak penetrating power.
Beta minus decay. This type of decay usually occurs with parent nuclei rich in neutrons. The general equation for beta minus decay, XAZ decays into YAZ plus 1 plus electron plus a particle called antineutrino. The antineutrino has no charge number and no mass number, has an extremely small mass, does not interact with matter, and moves at a speed equal to that of light. If the daughter nucleus is produced in an excited state, it returns to the ground state directly by emitting one photon or in several steps by emitting more than one photon. The emitted electron is not an orbital electron. It is formed inside the nucleus according to this neutron decay equation. Neutron decays into proton plus electron plus antineutrino. By neglecting the kinetic energy of the parent and the daughter nuclei, then the liberated energy, which equals delta mc squared, equals the kinetic energy of the emitted electron plus the energy of the antineutrino plus the electromagnetic energy carried by the gamma ray. Example, carbon 14 decays into nitrogen 14 plus electron plus antineutrino. Look at this animation. An electron can penetrate the sheet of paper, but it is stopped by the sheet of aluminum. This means electron radiation has a strong penetrating power.
Let's move to the beta plus decay. This type of decay usually occurs with artificial parent nuclei which are rich in protons. This is the general equation of the beta plus decay. The parent nucleus decays into the daughter nucleus by emitting a positron and a neutrino. If the daughter nucleus is produced in an excited state, it returns to the ground state directly by emitting one photon, or in several steps by emitting more than one photon. Now, the positron is also called the anti-electron. As we have seen in a previous slide, it has the same charge as a proton, but the same mass as an electron. Thus, characteristics of a neutrino are similar to those of an antineutrino. The emitted positron is formed inside the nucleus according to the proton decay equation. So inside the nucleus, a proton decays into a neutron, a positron, and a neutrino. By neglecting the kinetic energy of the parent and the daughter nuclei, the liberated energy in this decay would be the sum of the kinetic energy of the positron, the kinetic energy of the neutrino, and the electromagnetic energy of gamma rays. As an example, carbon-10 decays into boron-10 by emitting a positron, a neutrino, and a gamma ray photon. Beta plus has a strong penetrating power.
Consider a sample of a radioactive isotope whose number of nuclei is N0 at time 0. Observe the simulation in the adjacent figure. The radioactive substance decays or disintegrates, so the number of nuclei decreases with time. At an instant t, the number of undecayed or the number of the non-disintegrated nuclei is n. N is given by n0 e to the power minus lambda t, which is called the radioactive decay law. Lambda is a characteristic for the radioactive isotope, and its SI unit is second minus 1. Multiplying both sides by the mass mx of each nucleus gives mxn equals mxn0 e to the power minus lambda t. Substituting mxn by m and m0 or mxn0 by m0, we get m equals m0 e to the power minus lambda t. m0 is the initial mass and m is the undecayed mass. The radioactive decay law shows that the number of the remaining nuclei and the undecayed mass decrease exponentially with time.
Now we are going to introduce a new physical quantity called half-life. It's a characteristic constant for any radioactive isotope. Let n0 be the initial number of nuclei in a radioactive sample at time 0. After a time t, half of the initial nuclei have decayed, so the remaining number of undecayed nuclei becomes n0 over 2. After another time interval t, half of the remaining nuclei decay, so the number of undecayed nuclei becomes n0 over 4. Similarly, after another time interval t, the number of undecayed nuclei becomes n0 over 8. T is called the half-life of the radioactive substance. By definition, the half-life T of a radioactive substance is the time needed for half of the radioactive substance to decay. T is constant and is a characteristic of the radioactive substance. Now let's derive the relation between the initial number of nuclei and 0, the number of undecayed nuclei n at time t, and the half-life T. At time 0, n equals n0. At time 1 half-life, n equals n0 over 2, which can be written as n0 over 2 to the power 1. At time 2 half-lives, n equals n0 over 4, which can be written as n0 over 2 power 2. At time 3 half-lives, n equals n0 over 8, which can be written as n0 over 2 power 3. But what if n half-lives have passed? Then n equals n0 over 2 to the power n. Small n is the number of half-lives. So to calculate small n, just divide the time interval given in the question by the half-life of the radioactive isotope. This formula has another form. We can use it as m equals m0 over 2 power n. So we can use it with numbers or with masses. To understand the half-life, watch this animation. Consider a radioactive substance. For clarity, we assume a very, very small number. So assume that n0 equals 32 at time 0. After a time of 6 seconds, which is equal to 1 times 6, the number of undecayed nuclei is 16, which is equivalent to 32 over 2 or n0 over 2 to the power 1. After a time of 12 seconds, which is equal to 2 times 6, the number of undecayed nuclei is 8, which is equivalent to 32 over 4 or n0 over 2 power 4. After a time of 18 seconds, which is equal to 3 times 6, the number of undecayed nuclei is 4, which is equivalent to 32 over 8 equals n0 over 2 to the power 3. So at each instant, n is of the form n0 over 2 power n.
Since lambda and T are characteristics of the radioactive substance, let us determine the relation between them. N equals n0 e to the power minus lambda t. And we know that after one half-life, the number of the undecayed nuclei becomes n0 over 2. So replace n by n0 over 2 and replace t by 1 half-life. Then n0 over 2 equals n0 e to the power minus lambda t. Dividing by n0 both sides, we get 1 over 2 equals e to the power minus lambda t. Then we can write 2 equals e to the power lambda t. Taking the natural logarithm of both sides gives ln2 equals lambda t. Therefore, t equals ln2 over lambda. A sample of 1 gram of uranium-238 takes 4.5 times 10 to the power 9 years to disintegrate and become 0.5 gram, whereas a sample of 1 gram of astatine-217 takes only 32 milliseconds to disintegrate and become 0.5 gram. This shows that the disintegration of astatine-217 is much faster than that of uranium-238. By definition, the activity of a sample is the decay time rate. It is the number of decays per unit time. Let's start with the average activity. We know that the number of the decayed nuclei equals the initial number of the nuclei minus the remaining number of the nuclei and can be represented by minus delta n, since delta n equals n minus n0. According to the definition, the average activity can be written as n decayed over delta t equals minus delta n over delta t. The SI unit of the activity is the becquerel. Its symbol is BQ. 1 BQ or 1 becquerel equals 1 decay per second. The Curie is another unit of the activity, equals 3.7 times 10 to the power 10 becquerel.
Now let's move to the instantaneous activity. The average activity equals minus delta n by delta t. As delta t approaches 0, the average activity approaches the instantaneous activity. Then we get the instantaneous activity equals minus dn by dt, where dn by dt is the derivative of n with respect to time. Remember that n equals n0 e to the power minus lambda t. So we need to differentiate this expression with respect to time to get A. This gives lambda n0 e to the power minus lambda t. Now this gives A equals lambda n because n0 e to the power minus lambda t is just n. Now we need to get A0. So replace t in this expression by 0. You get A0 equals lambda and 0 because e to the power 0 equals 1. Finally, this gives A equals A0 e to the power minus lambda t. So we replaced lambda and 0 by A0. This formula has another form, A equals A0 over 2 power n. So the instantaneous activity decreases exponentially with time. Now, an important remark. When delta t is much less than t, the activity can be considered constant during this time, which means that the average activity approaches the instantaneous activity. Hence, we can use minus delta n by delta t to calculate the instantaneous activity. For example, if the half-life is few millions of years and we are asking about the instantaneous activity of over 1 year, then when you calculate the average activity over 1 year by dividing the number of decays by time of 1 year, then this average activity could be considered as just the instantaneous activity.
In this simulation, consider the radioactive uranium-238 nucleus. This nucleus decays into unstable thorium-234 by emitting an alpha particle. Then, thorium-234 decays into unstable protactinium-234 by emitting a beta-minus particle. Next, protactinium-234 decays into unstable uranium-234 by emitting another beta-minus particle. This process continues with several alpha and beta minus decays, eventually ending with the formation of the stable nucleus lead 2O6.
A decay family is a series of radioactive isotopes in which each member decays into the next through a sequence of nuclear decays, ultimately ending in a stable isotope. So as you see, the uranium decay family ends with lead-2O6, which is stable. So the three naturally occurring decay chains are those of uranium-238, thorium-232, and uranium-235, also known as the actinium-227 decay chain, each ending with its own specific lead isotope, lead-206, lead-208, and lead-207, respectively. The only artificial decay chain is that of neptunium-237, which is an artificially produced element and ending with bismuth-209.